All right, good evening, everybody. Tonight we're going to talk about the definition of derivative and the power rule. The power rule is what we discovered on Friday, which makes our life extremely easier than using the definition of a derivative. But I will go through these first two problems with the definition of derivative in mind and then show you how it compares to the power rule. So the first thing is I'm going to use the definition of derivative to find what the derivative of x squared minus 2x is. Right? So I'm going to use this particular notation here. Now understand what this is saying is that the limit at h approaches 0, meaning that the difference between where I started, like x, f of x would be like x1, so x1, and then I'm adding a number, but it's getting very, very, very close to 0, which means I'm trying to zero in on that particular number I'm trying to find. So go back to what we've done with limits is the idea we need to do everything in our power to eliminate this h on the bottom. If we don't eliminate the h, then we're in trouble. Okay, so let's talk about this particular notation here. So what I'm going to do is I'm going to put x plus h into this particular function. So that's going to be, like I did in the board, I'm going to put this in different colors. So let's say this is x plus h squared minus 2. Actually, I don't know if that helps. Let me take a step back here just a second. I apologize here. I know you guys are busy people. Let's say, for example, I'm going to put this like this. Okay. Okay. So I'm going to put these in blue. So this is I'm putting x plus h in this function. Okay. So I'm putting wherever I see an x in for x plus h. And then this is where I said majority of people make their wrong answers is they forget that we are taking minus the function f of x, which means I'm going to rewrite the function f of x right here, x squared minus 2x. So I'm taking the function f of x, this is what f of x stands for, I'm putting it there. And then of course it's all over h, but I'm going to hold off on doing that until I kind of break this thing down a little bit. Okay, so now that you kind of see a visualization here, we're going to take x plus h squared. So that would be x plus h times x plus h, which would be x times x, which is x squared, x times h, which would be x h, h plus or h times x, which would be whoa, I'm getting kind of messed up here, plus xh, and then if I multiply these xh again, I get xh, and then h times h, which is h squared. All right, so that's and I'm going to simplify that to x squared plus 2xh plus h squared. Now, then I'm going to take minus 2 times 2x, and that negative 2 also applies to the h, so that would be minus 2h. And then I distribute this negative sign to each term here, negative x squared plus 2x. Okay, so I got all this jumbled mess of stuff. Okay, remember it's all over h as well. But you'll notice that I'm able to cross some things out to clean this up. So the h squared goes off, h squared is gone here, the negative 2h, negative 2h, and then I'm left with this kind of stuff. And I'm going to write this in descending order in terms of h. So I have h squared, let's see, h squared plus 2xh, I'm having trouble pronouncing that, minus 2h, okay? And then I'm going to factor out an h. It's my goal to factor out an h because I want to eliminate this h on the bottom. So if I do that, h comes out, I got h plus 2x minus 2, okay? So I'm going to put that h underneath there now, and you'll notice that now I canceled that out. Now let's get back to what we're trying to do here, which is the idea of limit as h approaches 0. Okay, so now I have this equation h plus 2x minus 2. Now if I asked you in the previous sense, what do I do now? Well, you would say, well, it's fine to plug in 0 for h because it's not a restriction or anything. So if I do that, I get 0. So it would be 0 plus 2x minus 2, which would give us a derivative of 2x minus 2. Okay? Which you guys know now the power rule that you could have just looked at this and easily said that, but kind of showing you the basis of how this stuff comes about. Okay, so now let's talk about just for a moment what this is saying. Okay, so this is saying the idea that I now have a formula. So the derivative of this function is 2x minus 2. Now what this derivative does, it allows me to find the instantaneous rate of change of anywhere on this particular graph. And we're going to talk about this tomorrow a little bit more when we got a graph up there talking about it. But let's say, for example, I want to know the instantaneous rate of change at x equals 5. Okay, so instead of having to do the average rate of change getting closer and closer to 5, we can just plug 5 into this, and so the instantaneous rate of change is at 5. Oop, let me create that a little bit. The instantaneous rate of change at 5 would be 8. Okay, now this instantaneous rate of change also tells me the slope of the tangent line at that particular point. Okay, now I could also type in what's the instantaneous rate of change of 5.5, 6.2, 3.8. We could put in all these different numbers at that particular time. What's the instantaneous rate of change? And it would be able to give us this little nice formula right here. Okay, so next thing on the list. Okay, let's say, for example, my function is 3x. And again, some of you guys are able to just look at it and say, oh, I know what the derivative is because I know the power rule now, which is great because that's a great skill to have here. All right. Let's see here. I'm just erasing away. I got to figure out. I say this every time I make a video, but I got to figure out a way to make this eraser a little bigger. Seems like I'm messing around here. All right, so next thing we're going to do is 3x. So let's say, for example, I have the limit at, let's see, we have 3x plus h minus 3x. Okay, now you're going to easily see what we're doing here. I mean, it's a line, it's a linear equation, so the instantaneous rate of change is going to be the same at every single space, or the slope of the tangent line. And again, we'll talk about this more tomorrow, but on this particular equation, again, this is over h. So we have 3x plus 3h minus 3x over h. And again, the h is approaching 0. But you'll notice that, oh, this cancels out and this cancels out, so I'm left with 3h over h, which would equal just 3. So my instantaneous rate of change at every position on this particular graph is 3. And you'll kind of, again, we'll bust out the GeoGebra tomorrow and we'll kind of look at that a little bit more. Let's see. Another problem here. Let's see. I do want to look at this problem because it associates with what we just, the standard we just got done with, which was the radical exponents. So we look at this and we have the square root of x. Now this particular square root of x, it doesn't really help it because it's tough to apply to the power rule because it's not written in exponential form. So that's why we're going to change this into x to the 1/2. Okay, now in this particular problem I'm going to use the power rule mostly because I will show it in both ways. I'll show the definition of a derivative tomorrow using this. But for this particular instance, we're going to take whatever the exponent is and put them in front. So now we have 1/2 times x. And then this is where it gets a little goofy, is we're going to take 1/2 minus 1. We always have to take 1 less than what the exponent is. Okay, so that means that our derivative, or not our derivative, our exponent is now negative 1/2. Now think about what that's saying, because again, we've worked with negative exponents as well, and we're going to write it into so that there is no negative exponent. So my derivative of square root of x is 1 times 2x to the 1/2, or a little bit more mathematical is 1 over 2 square root x. Okay, so that's the derivative in this case. Now please go back and watch that. Try to understand what I'm trying to get at here. I kind of reversed the things a couple different times, but kind of take a look at that. Now again, tomorrow we're going to look at the graphs of these, and I'm going to kind of more go in depth about what it means to find the derivative of something. So I think that's a very important thing. It's one thing to just be able to plug in numbers and find out what it is, but another instance to actually know what a derivative is. Okay, so attempt examples 4 and 5. 5 is a very unique problem, but I'm hoping you guys paid attention on Friday to figure that one out. So attempt 4 and 5, and then we'll talk about those tomorrow again with example 1 through 3. So thank you very much for paying attention, and I'll see you guys tomorrow.